Joe, welcome back, everybody. How's homework going?
Well, now that number three's worked out.
It's working?
Well,
It's in progress, yes. So you guys got my email about not really a glitch, but a difficulty in getting the output that you need. So these ones, enter the test statistic. It's not printing to 2 decimal places sometimes, for reasons that I don't know. So if you're using SAS, the way that these homeworks are built is that I run the models for all of your individual data sets and I store the results in data files, and that's where they pull the answers from. So it doesn't know how many digits are displayed on the output because it's pulling it from the saved tables. So the code that I sent you yesterday, ODS output, allows you to save that table to a data set, and then when you open it, you should be able to get the value with greater precision, 2 digits as required for this. So if it's not working for whatever reason, let me know, and if you have the right answer, I'll just give it to you. Like Terry's like, it was 0.2, and I'm like, I know it's right. Yes, it's 0.16, right?
I tried everything, and then when he sent it to me, I'm like, oh, I'm so stupid.
I just want like my wait.
That's what that's what I recognize. So yes, I'm sorry. I made the model too powerful. So because when your F hits like 10,000 or something, you really don't need the decimal places anymore. But so any questions on this from those of you who are working on it?
Yeah.
Yes. Okay. She's waving emphatically, so she gets to go first.
I don't know why I'm having such a hard time. So in section 2.
Okay.
Everything's going great, and then when you ask me to switch it and look for the hard opponent versus the easy opponent, because of how I don't know how to get that, and I can't figure out why. And then it's the same when you go down to the 3rd section, and then because easy's great and then hard is not, and I don't know, my brain can't figure it out right now.
Okay, so let me dwell on for a moment. Why is easy great and hard is hard?
Because of the way that I coded it. And so I was trying, and I was like, well, it doesn't make sense to create a new one and recode and do that. That doesn't make sense. If there's something that I can't remember.
So the instructions were for your type of opponent, it's easy versus hard. Easy was to be the reference group. So that means that the model gives you parameters for easy because that's when 0 is for the variable. So all simple main effects, the intercept, etc., those are for easy. To get what it is for hard, you have 2 choices. One of them is to switch your coding, make hard the reference group, and then all of the stuff directly from the model is for hard. That is a perfectly fine way to do it. A more efficient way that we've been working on, though, is to be able to write estimate or lincom statements to be able to get what it would be for hard.
I'm not writing the estimate statement right.
You're not writing the estimate statement right. Let me see here. Let's pull up, let me get one example here. The slope of verbal for hard, for instance. So would it help to go through one of these?
Oh, yes.
Oh, yes? Okay. So let's get the model going here. I got to remember my instructions. So section 1 is main effects, section 2 adds 2 interaction terms. Okay. So opening up Word equation editor, we've got Scrabble for person I equals, what comes first in my equation? Intercept, which is B0 or beta 0. I'm going to do the betas, make it fancy. Plus, the first effect that I gave you was beta 1 times, I'm going to do, let's see, easy versus hard with an I. And then we have beta 2 times verbal, centered at what in this story? 10? 30, okay. So verbal I minus 30 plus beta 3 times spatial I minus 10, right? Okay. And so that's the first model. So that's what it would look like for section 1. So each of these effects is an additive effect. It stands on its own, in other words. But if we add what the 2 interactions that are implied for section 2, I'm going to cheat a little bit here. Copy, paste. Let's make that come down. This is going to be beta 4, and it needs to have this next to it. And then we need one just like it for spatial. -5 and spatial -10. And there's also an E, but that is inconsequential for most of the questions. Okay, so here's my model. I find it helpful to write this out to start with, just so that you know what all you have. But another way to think about it is, with the exception of beta 0, each of these words referring to your predictors is in your model statement. So you can look up there and it'll be the same sort of visual representation of what all you have to think about. So in this model, the intercept is when all the predictors are 0, right? So that's for the easy type of opponent, when verbal is 30, spatial is 10. Once we pick up these interaction terms, each of the main effects that they go with becomes conditional, right? So this easy versus hard is specifically the difference between opponent types if verbal is 30 and spatial is 10, right? And so beta 4 and beta 5 are the interaction terms. They can be interpreted one of two ways. You can talk about how the effect of verbal and spatial ability differ between easy and hard opponents. That's the way that this version of the story is. So beta 4 and beta 5 are differences in the slopes of verbal and spatial. You can also think of it as how the difference between easy and hard differs as a function of verbal ability or spatial ability. So that's the other way that is equally correct to think about it, but I didn't ask any questions that way. So if I want to know what, say, the slope for verbal is, we did this in our quiz, yay? Mm-hmm. So let me get this all organized so I can see it all. No, left, thank you. Stop it. There. So slope for verbal. Step 1, what do I do?
Look for verbal.
Get all the verbals. I need that one. Need that one. Okay. Now what? Factor out verbal, yep. Factor out verbal. So do my copy paste here. So that means take this, and get rid of it. Take this, and get rid of it. Let's see if it'll let me do brackets, sure. They're not pretty, but they'll work. And we stick verbal in the back like that. So now I know how to get my verbal slope as a function of any type of opponent. So this linear combination right here is the basis of your estimate statement to get the verbal slope for any type of opponent. So if I were to do, let's say, easy, which is easy because I don't actually need to write it, which is why I can give this to you. So we'll do estimate verbal slope for easy. Then I need the word for the predictor that corresponds with that slope. So beta 2, I need verbal, like in my code it's called verbal 30, because I'm not, imaginative that way. And I need how many of those? How many beta 2s do I need? Just one. That will always be the case, by the way, because the first term in these statements is the thing you're trying to estimate. So you just need one of those to get it started. But I also need, we'll call it, let's see this, E versus H times verbal 30. And if I'm filling this in for easy, what value do I need for this variable right here? Given your coding instructions. What did I tell you to code the easy group? 0. So, done. And this is why easy is easy, because this one is not actually a linear combination. It is what beta 2 means, and beta 2 is already given to you directly in the output. We'll do a bonus. Okay, so if I have hard, the first part stays the same, but now what number, based on my coding scheme, do I need to put here? It's 1. Yeah, so if you're using 1 and 2 instead of 0 and 1, your answers are not going to work. So make sure it's the 0, 1 version of the variable, and a 1 goes there. What would happen if I forgot, for instance, 30? No, it should yell at you. It will say, predictors listed in the estimate statement must have appeared in the model statement. So if you see that, it means you spelled something wrong. Or put the wrong version of that. So it has to all match. Okay, does that help? Okay, the process for getting the spatial slopes is remarkably similar. It's a find and replace, which is Control H in SAS, by the way, and I believe it's Control H in Stata as well as a general Windows command. Okay. So let me see what other types of questions we might want to talk about here. Okay. Other questions on section 2? Why are there so many cupcakes left?
They're very good.
You heard it here first. Don't be shy. You're starving graduate students, right? You need your sustenance.
I actually had lunch like less than 15 minutes.
Okay, so I'll check again in like a half hour or so, right? I will tell you that I deliberately ordered these in such a way that the answers follow one another. So for instance, here is the slope of verbal for easy, and then there's the slope of verbal for hard, and then there's the difference between the two. So if you know how to get each of them, you know how to get the difference. If I were to do that here to complete the set, do you remember how to get the difference? That would work, although an estimate statement would work probably more straightforwardly. If you know how to get the slope for each, you know how to get the difference because it's literally a question of subtracting one of these lines from the other. So I always do it easy versus hard. This is the direction that the subtraction would go, so I'm going to move these for you. So estimate diff in verbal slope, E versus H. Okay, 1 minus 1 is?
0.
Okay, that's gone. 1 minus 0 is?
-1.
1 minus 0 is?
I was like, wait a minute, why am I wrong?
Because I'm very wrong.
So
Oh, gosh.
if I literally subtract these lines, this is what I'm left with. In other words, the difference in the verbal slope between easy and hard is a model parameter. That is what the interaction term means. So I didn't even need to write this. But showing it this way, I think, helps give you the logic of what we're doing a little bit. That will not always be the case. So learning how to write out each piece to get the difference, I think, is useful as a more general strategy. But in this case, it does simplify to just this one term to get the difference. Okay. Section 3. You have 2 strategies for this. You can make fake people and re-estimate the model from section 2, save the fake people to a data set, and copy the answers. Or you can write an estimate statement for each of these estimates, and its standard error will pop out right next to it. Things to think about here. So here's one. Do you want to do one of these? Would that be good? Without the fake people. Let's do one. So here's my model. I'm going to move this stuff down for a second. By the way, it might be helpful if you estimate. Okay, I can't type today. Estimate. There we go. You can literally paste in the questions as you save yourself some typing. So what does the estimate statement need to have in it in order to create a predicted outcome? Only some of the stuff or all the stuff? Excuse me, fixed effects is what I mean by stuff. Be more specific. Do I need all of them or only some of them to create a predicted outcome? There. So do I need all the fixed effects to create a predicted outcome or only some of them? Not meant to be a trick, I swear.
All of them?
Yeah, because the model tells me how my outcome gets predicted, right? I can't just leave out some of them. It won't be the same model. So then I need intercept 1. If it's for easy, I need easy versus hard is what? 0. I need verbal 30 is what? And don't say 15. Minus 15, right? Because it's centered. Did that catch anybody? Yep, that's a common mistake. That's an easily fixable one. Likewise, spatial 10, negative 3. And then we need both the interaction terms. I'm just going to return here. And easy by verbal. And we also need easy by spatial. And how do I know what numbers go here? Like, what goes there? Why is it 0? Because 0 times anything is 0. That's why.
Oh, that's why I made it wrong.
Likewise, 0 here, because anything times 0 is 0. If we did, let's take this and do hard opponent. What needs to change? Does intercept change?
Nope.
Oh. Does easy versus hard change?
Yes.
What is it now?
1.
1. And because that changed, what now goes here? Yeah, 1 times negative 15 is negative 15. And 1 times negative 3 is negative 3. So the interaction terms only turn on if you're talking about the hard group. Otherwise, they 0 out. So once you get the pattern right, you will find these very easy to finish just by swapping out the values. Getting the pattern right is the hard part. Okay. And because I don't have that level of programming skills, you don't have to make a picture. I haven't figured out how to have you make a picture and have it be graded automatically. So, but that would be the next step, is to make some pictures, right? It might be nice to have a what the verbal slope would look like for the easy group versus the hard group in one picture, what the spatial slope would look like for the easy group versus the hard group in another picture. That would be the kind of thing you'd want to plot. Okay. Other questions? Yes, but you can ask them.
I think you just said it. But when we have to do the thing where it's model against model, like the test statistic for the model when you add the new thing. And I tried
Yes.
to copy and paste my stuff from homework 5. I mean, obviously changing the variables, but I just am still, but I think it's because I messed up my opponent, putting my opponent stuff correctly in the code.
Possibly.
Yeah, so that's why I was like, kind of have a question, but not one.
So those sorts of questions, you want to talk about those? Would that be helpful? So in general, you can list whatever combination of fixed effects that you want and ask for whether or not they are significant as a set. That is the basis of the F-test for your R-square. So if I wanted to do that to duplicate what the model is giving me by default, I would write what is known as a contrast statement in SAS, or it is a test statement in Stata. The code is a little bit different, so we'll do SAS here. If I did contrast model R-square F-test, right, it would be all of the terms with just ones. And each term would be separated with a comma to denote the degrees of freedom in the numerator, meaning the number of slopes being tested simultaneously. If you forget your commas, it ain't gonna work.
So the interaction terms are also included. Okay.
Yeah, so so this is given to you by default. All programs will give you an F-test of the model. But if I wanted to recreate it, it would look like this. I'm missing one. Each fixed slope in the model gets a 1 with a comma behind it. The same thing in Stata. Looks like this. It goes test. It doesn't let you put in a label, which I hate, by the way. So we got to do that as a comment, excuse me. It goes like this, parenthesis equals 0 for each. Equals 0, like that. So if you do this same thing every single time. So the questions that are asking about the contribution of the interaction terms to the model specifically rely on this same principle. We know based on the output for each interaction term individually, that's known as a univariate wald test. We know that t statistic that gives us the p-value, whether it's significant or not. But what we don't know is if they work together as a set to improve the model R-square, because that also includes whatever covariance they share between them to answer that question. So instead of listing everything, if you want an F-test for how the new stuff specifically improves the model, then your contrast only needs new stuff in it, which means all of that goes away. We also did the same thing when we have categorical predictors with 3 or more groups to get an F-test for the overall effective group, lumping them back together. If we get to our example today, you'll see another instance of that as well with the dementia group stuff. Okay. So does that help, Kelly?
Yes, it does. Thank you.
Excellent. Other things I can help with, I'm happy to do so. There is nothing in here that we haven't done. So no Googling, right? Go to your own stuff and try and find it first. The Google just leads you astray. Other questions? No? Okay. Can I tell you a story? So it turns out that social media is filled with a lot of inaccuracies. And I'm kind of addicted to Facebook at the moment. It's my number one way to procrastinate on doing anything. So I have a conversation that I participated in last night where someone in one of the groups I'm part of was asking, can you, in simple terms, tell me how ANOVA and regression are alike? I was trying to come up with an analysis, and someone told me that you can do it all using general linear regression, but I thought ANOVA and regression were two completely different things. Can someone help? So how would you answer the question? Let me ask you that. Someone comes up to you and says, how are regression and ANOVA the same thing? I don't get it.
Can I take a stab?
Yeah, please.
Regression is with a quantitative variable,
Predictor, yes.
predictor,
Mhm.
and ANOVA is with a categorical or binary variable.
Correct.
So they're different.
But they both predict a quantitative outcome.
Dang it.
So in that sense, they're variants of the same idea. So she had it partially right when she said general linear regression. It's general linear model. And so there are many different labels that are like flavors of the GLM, and it's exactly what you said. If it's quantitative predictors, it is considered regression. Multiple regression, if you have more than one, or simple regression. Sometimes the word linear gets thrown in there to differentiate it from other kinds of regression that you're going to learn about next semester if you come back. If you have one binary predictor, that's called an independent samples t-test. If you have a predictor with 3 or more categories, that's a one-way analysis of variance. So they're just labels for different types of models, but they're all the same umbrella. And so then we get into the people who tried to help out. And so most of them hit on that sort of theme, but then there were also comments that I felt didn't help, like regression predicts, but ANOVA identifies differences among groups. Now, why would that make me bristle? Regression predicts, but ANOVA identifies differences between groups. Let's look at the model that we're playing with right now. We are predicting Scrabble scores from a couple different kinds of predictors, right? One of them happens to be categorical, or binary in this case. Two of them happen to be continuous. So arguably, you're always predicting, no matter what kind of predictor you have, right? Like, that's the whole point. In terms of interaction terms, this is where it gets interesting. By default, in a regression class, interactions are not included. You only include them if you have hypotheses that dictate them. And so it's not at all a usual part of doing business. If you do ANOVA in ANOVA software, by default, it spits out all possible interactions. ANCOVA allows interactions between quantitative predictors, but not quantitative predictors with categorical predictors. So there's all these conventions that literally are tied to like the software program you use. It reminds me of a story about a pan with a ham. Have I told you guys about this? I thought it was an apt analogy. So the story goes, there was someone who was watching her mom was baking a ham, and she cut off like the last 2 inches of it. And she's like, why did you do that? She's like, well, I don't know. My mom always did that. So ask Grandma, why did you cut off the last 2 inches? I don't know. My mom always did that. Go to Great Grandma. She said, because my pan wasn't ever big enough to fit the whole ham. And that's why if you don't know the rationale, you just sort of follow practice. And a lot of, I think, confusion about when a model is the same or is not the same boils down to how it gets used, decisions made by the software and not you. So one is not harder or easier than the other necessarily, but the software may make it more complicated if it adds stuff to your model that you didn't explicitly ask it to. So I couldn't help myself. I had to chime in. I couldn't take it. But I did send her to this class. So if you're watching, we're talking about general linear models in a nice real-world situation. What else did I want to talk about? I don't remember. So, questions on anything else related to homework? We'll shut the door on this if not. No? Okay. Office hours starting at 3:15 today. Email questions are always welcome as well. Then we will take that away. And I was trying to debate where to start. I wanted to start with how to do interactions among categorical predictors. This is example 8. Yeah, you're not thrilled about it though, are you? Because I want to show you one model because it rounds out our collection of how to handle interaction terms. More generally, this is what it takes to fit interactions among predictors whose main effects are characterized by more than one fixed slope. That's sort of the more general concept. So this is example 8. The model for us right now, it's the same data set we've been playing with. We have age, grip strength, gender, and 3 groups of dementia. So all of the coding to set up the predictor variables is exactly the same as what we had before. And this is the model that we're talking about. So in example 6, we built up to each predictor having a main effect. In example 7, we added an interaction of age and grip strength, which is the concept you're now getting to practice in your homework. And so the new pieces here are underlined. Beta 7 and beta 8 are the interaction terms between gender and dementia. It takes more than one interaction term because dementia has 3 groups. So just as it takes 2 contrasts to fully differentiate the 3 possible group means and then get all their differences, it takes 2, I'm going to call these interaction contrasts, to differentiate how the effect of gender varies by dementia group. So all in all, this table of estimated means here, so these are conditional on age 85 and grip 9, give you 6 possible categories. So there are 6 values to be recreated by this model. One of them is given by the intercept. It's going to be based on your coding scheme, which one that is. In my coding scheme, for gender, men are the 0 and women are the 1. And for dementia, none is the reference group, dem NF is none versus future, and dem NC is none versus current. So that means that that cell right there is my reference cell. So I'm switching terms a little bit. A unique combination of 2 or more predictor variables that are categorical, these are referred to as cells, cells of the design. So that's what my intercept means. The main effect of gender here, beta 3, because it's part of an interaction with dementia, it takes on a special conditional status, right? Simple slope or conditional slope. That beta 3 main effect of gender is going to be specifically when you're talking about the none group. So beta 3 is going to give me the difference between these 2 cells right here. Okay, with me so far? Or maybe you're like not, like, aren't we done yet? No, it's I can't like not give this to you. I got it. I'll leave remiss. So likewise, beta 4 and beta 5. These are dementia group differences conditional on gender equals 0, which is for men. So beta 4 gives me the difference between men who don't have dementia and men who have future dementia. That's beta 4 is the comparison of those 2 cells. Beta 5 is men who are none versus men who are current. Last but not least, in the context of categorical variables, the phrase that I learned and which I still think is useful to talk about what those interactions mean is that they give you different differences. It's how the gender difference differs by dementia group, or how the dementia difference differs by gender. So this first contrast here, sex by dementia NF, is going to tell me how this difference right here, this 6-point difference, differs from this 6-point difference. Spoiler alert, do you think a 6-point difference differs from a 6-point difference? Not at this sample size is the answer, right? It could. If I had 1 million people, then I'm, 6.000 versus 6.001, like that could be different. That would be a very small effect size, probably, but it could still be significant. The other one then says how this, doing math in my head in front of you, 12-ish point difference differs from this 20-ish point difference. Are 12 and 20 different? Probably. We'll find out. So through these interaction contrasts, if I know how the gender difference differs by dementia group or vice versa, I can get to the rest of the missing simple effects and means. Another way to think about it is that these 6 distinct means are going to be perfectly recreated by the intercept as 1, beta 3, beta 4, beta 5, beta 7, and beta 8. 6 cells, 6 fixed effects in the model. So you got them all. So even the differences that are not directly given by the model parameters, you can ask for after the fact, because they're all in there. So here's what we would do to get all of those pieces of information. So here's my model. I have rearranged it so that the effects of gender and dementia group are next to each other. So we have the 3 continuous variables that we already talked about. We're going to set those aside for now and just focus on this set right here. These 2 contrasts are an example of what we just talked about with respect to your homework, the idea of contrast new stuff, or more generally contrasts of multiple things put back together. The first one gives me the overall simple main effect of dementia, lumping the 2 main effects back together again. So it's, is there a difference among any of the 3 dementia groups in men? That's what that is. The second one asks, is there an interaction of gender by dementia? So if this is significant, we have to figure out which of these is doing it, as well as the third that's a linear combination of the other 2. I have fake people in this data set, so this, if you're interested in learning how to do that, this is the extra piece of code that you need to add. It creates a new data set, in this case in the work library, called predicted outcomes. It has a column of predicted outcomes that I have named Y hat. It has a column of standard errors for the predicted outcomes that I have named SEY hat. Otherwise, if you don't do this and you want to know what the means are for each group, here's an example of estimate statements that would give you that. Note that because age and grip are not here, we're treating them as if they're set to 0. So all of these are conditional means for somebody who is 85 with a grip strength of 9. Then we get into simple effects. So there are 3 possible types of gender differences implied by the model among the non-dementia group, the future dementia group, and the current group. Likewise, there are 6 possible simple effects of dementia. So there's none versus current, none versus future, and future versus current in men and in women. So these lines here get me all of the most interesting pairwise differences among the 6 cells of this table. In theory, if there were others that I wanted to know, like if for whatever reason, if I wanted to know if the men none cell differed from the women future cell, I could ask for that. I don't know what that would mean because they differ in two different ways at the same time, but in theory, you could ask for that. So that's sort of the traditional approach, is talking about each of these pairwise differences. Whether or not the pairwise differences differ is the interaction term. And so I have written out for each interaction contrast 2 possible interpretations. So the first 2 lines here is an interaction effect given directly by the model. This is just sex by dimension, none versus future. What this is telling us is whether or not the sex effect differs between the none and future groups, or, equivalently, whether the difference between none and future differs by sex. Same story for B. It's the other interaction term by itself, so it's none versus current, but it's the same idea. And the one that's missing is a linear combination of the 2 interaction contrasts. That is whether the sex difference differs between future and current, or whether the future-current difference differs across genders. So here's the analogous data code. I've written everything out. The only thing that looks a little bit different is margins allows you to go across a range of values rather than just have one line per predicted value, and test uses parentheses instead of commas to delineate numerator degrees of freedom. And there's that stuff. So my results then let's play, shall we? We shall. I'm keeping an eye on the clock. We'll play for like 3 minutes and then I'll give you the rest of the time to fill out your evaluations. 3 minutes. What are the 4 kinds of interaction terms again?
More positive, less positive, more negative, less negative.
Yeah, that. Okay. So the gender difference right here. This is in the none group. The fact that it's negative means the group that's coded 1 is lower. So that's the women. So women are lower by men in the none group by about 3 points. The first interaction contrast, you get this one highlighted and this one. In the future group, that negative effect of gender is
Less negative.
less negative, smaller, blunted, diminished, but not significantly. Likewise, this is the gender difference in the none group. In the current group, that negative gender effect is
More negative.
more negative, bigger, stronger. I'll skip the Britney Spears impression just for today. I can go the other way. This is the difference between none and future dementia in the men. This interaction term does what to it in the women?
Less negative.
Less negative, smaller. And this is the difference between none and current in the men. In the women, what does this interaction term do to it?
Less negative.
This,
Dang
yeah,
it.
yeah, this is a more negative, bigger.
Oh, God.
Yeah. And the one that's missing is the difference in these 2. That would be how the gender difference varies from future to current, or how the future current difference differs by gender. So the extra stuff, stop it, is all right here. So now you know how to do categorical interactions. Remember the coding trick that I taught you at the very end of last time? The class statement, where you don't have to write all this stuff out? Here's why I don't like it. What you get by default when you invoke that class statement is the marginal effect of each main effect rather than simple. Meaning that it gives you a test of whether the dementia group differences averaging over gender are significant. It gives you the same idea marginally whether the gender difference averaging over dementia is significant. And then it gives you an F for whether or not there's an interaction term. It doesn't actually tell you anything that you'd want to know. You still have to ask for it. So the rest of this handout is showing how the code to do this exact same model would differ. There's some pictures. If I treated dementia group as categorical, such that I had to provide values for each possible level everywhere, and left sex as continuous, versus the very last model, in which sex and dementia group are treated as categorical both, and it ends up that most of the default output that you get is useless. People don't know that, but you will. So there is a reason why I didn't give you the class statement, because I want you to think in terms of models and not marginal main effects. And as always, words. So here's some words for all of that. I'm bummed that we didn't get to the rest of the nested effects, but if you're ever in a situation where a predictor is only relevant for a part of your sample, that's what this is about. So I had a little bit of stuff about that. Those are called nested effects. They show up in multivariate models, and they show up in the presence of missing dementia, things like that. Like if you had a sample of men and women and you wanted to put in there like number of children you've given birth to, that variable is going to be missing for men, right? So you could make it a predictor only for women with this approach and still put it in the model. It's called a nested effect. So it looks like an interaction term, but what happens is you leave out the other main effects so that it's not an interaction, it's a nested effect. So that's what I want to do. Okay, so here's the plan, kids. You have the rest of the time to work on your evaluations. I just want to say thank you for all of your work this semester. It has been a lot of fun being here with you. I know that you all started this a little scared. Hopefully now you feel a little more confident. Don't be a stranger. You have earned the right to ask me questions for the rest of your lives by being here. So if you ever find yourself needing some sort of stats help or recommendation, let me know, because I can probably point you to something somewhere on my website that will help you at least get you started. So don't be strangers, don't be afraid of taking more classes, and thank you for everything that you've done this semester. Can we clap it out? Can we clap it out? All right. So I am going to go hang out there with my laptop. So if anybody wants to chat with me on your way out, otherwise, have some more cupcakes, and hopefully I'll see you next semester.
Thank you so much.